Hello. So, till the last class we have discussed about the histogram based technique for probability density estimation, and we have started our discussion on kernel based technique for probability density estimation. And after discussing about the histogram technique, when we started the kernel based technique for probability density estimation, you have noticed that in histogram based technique, what we do is we divide the feature space or the vector space into a number of cells or bins, where every cell or bin in one dimension or two dimension. In case of one dimension, it has a certain length or certain width. In case of two dimension, it has got certain area. In case of three dimension, it has got certain volume, and when we move above three dimensions, say dimension 4 and above, we call them as hyper volumes, and accordingly we can define the volume of every cell or every bin. And then the density multiplied by length or the area or the volume, we have said that this should be equal to the fraction of the samples, the fraction of the feature vectors which are given for training purpose. So, this probability density multiplied by width of the bin in case of one dimension, or the probability density multiplied by area of the bin in case of two dimension, or it is the probability density multiplied by the volume of the bin in case of three dimension and more dimensions, that should be equal to the fraction of the samples falling within the bin. And accordingly, we can find out that what is the probability density function in that particular bin. And our basic assumption was that within the bin, we assume that the probability density function is constant. So, once we do that, then we can find out, we can estimate what is the probability of a sample falling within a bin, because we know what is the probability density function, value of the probability density function within the bin. And then we have said that we have got other estimation technique, that is the window or kernel based technique. And so, what we are going to discuss now is the window or kernel based technique. So, in this window or kernel based technique, what we have said is each sample, each feature vector is a representative of a probability density function. And this probability density function has to be so normalized that the total area or the total volume under the probability density function remains equal to 1. So, in the simplest case, if we assume that every sample represents a probability density function, where the probability density function is a delta function. So, we started with an example. We said that suppose we have got, let us take a very small example. So, we have got samples. I assume that I have a single variable or a scalar variable x, and the samples which are given for estimation of the probability density function, those samples are say x equal to 1, x equal to 2 and x equal to 4. So, using just these three samples, we want to estimate the probability density function, and I assume that every sample represents a probability density function which is a delta function. So, a delta function has a very small width and certain height, and because we have got three samples at 1, 2 and 4 for estimation of the probability density function. So, we have three such delta functions, and the total area of these delta functions have to be equal to 1, which means that area of an a single delta function, area under a single delta function has to be equal to 1/3. So, I have a situation something like this. I have this variable x, and on this axis I put probability of x, and I have x equal to 0 here, x equal to 1 here, x equal to 2, 3, 4, 5 and so on. So, here you find that if a sample at location 1 gives a probability density estimate which is a delta function, so this probability density estimate will be something like this. Similarly, at 2 it has a probability density estimate which is something like this. At 4 it also has a probability density estimate something like this. And the total area of these 3 delta functions have to be equal to 1. So, that clearly means that area of each of these probability density functions have to be 1/3, because we have 3 such delta functions. Now, I can have situations something like this, that I can have more than one samples or more than one instances of a single value of x. So, I can have a situation something like this, that I have x samples of x, one at location 1, 2 samples or 2 values of x which are 2, and I have 4. So, now I have 4 samples of x, and using this 4 samples of x, I have to estimate the probability density function. So, because I have 4 samples of x, so I will have 4 such delta functions, and the total area under these delta functions have to be equal to 1. So, the delta function or the area of the delta function for a single sample obviously has to be 1/4. So, given this, I will have a situation of this form. I will have, so on this side I put probability of x, this is my x, this is 0, 1, 2, 3, 4, 5 and so on. So, I have one delta function at location 1, I have 2 delta functions at location 2, because you see that I have 2 samples of x, both of them having value 2. So, I have 2 samples at location 2. So, here I have 2 samples. So, the height of this delta function has to be double, and I have one sample at x equal to 4. So, this is the kind of situation that I have. And if the width of every delta function is a delta and area has to be 1/4, so height of every delta function, if it is h, I have h is equal to 1/4 delta. So, here this is 4 because I have 4 samples to estimate the probability density function. If I have n number of samples, then this h will be 1/n times delta. So, here the height of this delta function will be h, height over here will be twice h, and height over here again will be h. Now, when I have such a kind of delta functions to be used for estimation of the probability density function, you find that I do not get a smooth probability density estimate, or in other sense that this is not really suitable for estimation of continuous probability density function. So, if I want to estimate a continuous probability density function from the set of given samples, this choice of delta function is not a good choice. So, instead of using this delta function, what I can use is a window function or a kernel function. And the window function or the kernel function, these windows can be of different types. I can have a rectangular window, I can have a triangular window, or even the window function can have the shape of normal distribution. So, depending upon the choice, I can use a rectangular window. So, rectangular window will be something like this. Of course, it will have certain width and certain height. So, if I decide, if I fix the width of the window, then the height of the window will actually be determined by the total number of samples which are available for the probability density estimation. So, if I have total of capital N number of samples, I will have n number of such windows, and the total area of all these windows taken together has to be equal to 1. So, the area of a single window, area under a single window, so I will write area under a single window will be 1 upon n if n is the total number of samples which is given for probability density estimation. And from here you find that as I have fixed the window width of the window function, which is w. So, the area of under this window is w times h, which will be equal to 1 upon capital N. So, naturally the height of the window function h will be equal to 1 upon w times n, where w is the width of the window and n is the number of samples which are given for probability density estimation. Now, instead of this rectangular window, if I use a triangular window, let us see what kind of window we have. So, if I use a triangular window, triangular window will be something like this. Again, this triangle will have certain width and certain height, and if I fix the width to be w, then height h of this triangular window will be determined by again the number of samples. So, again if I assume that I have total n number of samples given for the probability density estimation, then area under a single window, I have total n number of samples, and so I will have total n number of such windows, and the area of all these windows taken together has to be equal to 1. So, area under a single window will be 1 upon n. So, over here if I compute the area of this triangular window, area of the triangular window is nothing but half into w into h, and which has to be equal to 1 upon capital N. So, from here I can compute the height of the triangular window h, which has to be equal to 2 upon w times n, where this w is the width of the window or the length of the base of the window, and h is the height of the window. So, every sample represents a probability density function, where this probability density is given by such a triangular probability density having base width is equal to w and the height is equal to h. I can also have a normal density function to represent the probability density given by every individual sample. Okay. So, these I can have other types of window functions as well. This is not all that I can use. However, these are the simpler ones, and we will explain our concept of windowed technique for probability density estimation using either a rectangular window or a triangular window. So, let us take the same example of 3 samples. I have this scalar variable x having sample at location 1, a sample at location 2 and a sample at location 4. Right. So, what I will do is, I will first use this rectangular window and see how this probability density can be estimated using the rectangular window. So, I will plot estimated probability density P of x, and because it is estimation, instead of writing P x, I will write P hat x, because I exactly do not know what is P of x. And along the horizontal axis or along the x axis, I will put this scalar variable x. So, this is 0, this is 1, this is 2, this is 3, this is 4, this is 5 and so on. And initially, I will use a rectangular window, and let me assume that the width of the rectangular window is equal to say 2. Okay. So, I use a rectangular window and width of the rectangular window I assume to be 2. So, this is my width W. And as I said before, that because I have got 3 such samples, so area of individual window has to be 1/3. Okay. So, accordingly I have to compute what is the height of this rectangular window. So, the height of the rectangular window h times W, that has to be 1/3, 1/3. So, height has to be 1/3 times W, and in this case W is equal to 2. So, this will be 1/6. And now, let us place such a window of width 2 and height 1/6, one at each of the sample locations. So, I have one window of width 2 and height 1/6. This is 1/6 at location 1. At 2, I have another sample. So, at location 2, I have to put one such window again. So, that window, let me use different colors, will be this. Height remains same, 1/6, and the window spans from 1 to 3, because width of the window is 2. And the same window I also place at location 4. So, I will have a window something like this. It spans from 3 to 5. So, once I have this, sum of all these areas gives me an estimate of the probability density function, right. So, if I add them up, you find that from location 0 to 1 in this range, I have got only one window. So, height of this window will remain 1/6. Then from location 1 to 2 in this region, I have 2 windows which are superimposing. One window which was placed at location 1 and the other window which was placed at location 2. So, these 2 windows overlap. So, obviously, here the probability density will be the sum of the heights of the individual windows. So, here it was 1/6. So, at this location, this height will be 2 into 1/6, that is 1/3. And from 2 to 5, the height will be 1 by 6. So, this red line or the red curve gives me an estimate of the continuous probability density function as represented by these 3 samples at location 1, 2 and 4. And now, if you compare this with this one that we did earlier with delta function, you find that this probability density estimate is not a continuous probability density estimate, but it is a discrete probability density estimate. Say for example, if I want to estimate what is P 3, here it will give P 3 is equal to 0, because the delta functions do not span up to x equal to 3. But in this case, when I use an window function or a kernel function, I can say that P x equal to 3 will be equal to, which is height of this probability density curve, which is equal to 1 upon 6. Whereas over here, if I want to compute what is P of x equal to 1.5, that probability that x is 1.5, which is given by 1 by 3. That is the height of the probability density curve in the region 1 to 2. So, I can use this window technique for such probability density estimate. Now, if I want to compute what is the total area under this probability density curve, you find that from here to here the area is 1 upon 6, because height is 1 upon 6, width is 1. So, area is 1 upon 6. From here to here the area is 1 upon 3, and from here to here the area is, I have 1, 2, 3 different segments of length 1, each is having an width of 1 upon 6. So, it will be 3 by 6, which is nothing but half. Okay. So, if I add all these two, I will get the total area under this probability density curve. So, this was a very simple case when we have used a rectangular window for estimation of probability density. Now, let us see that for the same example. Okay. One more thing, what will happen if I get multiple number of samples at a particular location. So, before I go for use of other window functions, let us see that what will happen if I have the samples as 1, 2, 2, 4. If I use this, then obviously I have to place 2 windows at location 2, and total number of samples that I have is 4. So, area under every window will be 1 upon 4, and let us assume that width of the window I use the same, which is equal to 2, right. So, width into height has to be equal to 1 by 4. Now, this width is 2. So, height of every window will be 1 upon 8 instead of 1 upon 6, which we had over here, which we had when we had only 3 samples. Now, we have 4 number of samples, though there are 2 samples at x equal to 2. So, when I have this, now let us try to estimate the probability density. I have x, I have the estimated probability density p hat of x. Okay. So, again let us put 0, 1, 2, 3, 4, 5, 6 and so on. Okay. So, here what I will do is I will put an window of width 2 and height 1 upon 8 at location 1. So, this window will span from x equal to 0 to x equal to 2. I place two windows of same height and same width at location 2. So, I will have one window and this will span from x equal to 1 to x equal to 3 because width is 2. So, this is one window and this is another window. And then I have a single window at location x equal to 4, again of height width 2 and height 1 upon 8. So, this window will span from x equal to 3 to x equal to 5 because width is equal to 2. And now, if I combine all these windows together, that is what is going to give me the probability density estimate. So, here you find that I had only one window, this is 1 upon 8. Here from 1 to 2 in this region, there are 3 windows which are superimposed. So, in these locations, the height of the probability density that will be 3 by 8. From 2 to 3, I have 2 windows which are superimposed. So, here the height will be 2 by 8. And then from 3 to 5, I have a single window. So, height will be this. So, this is what is my final probability estimated probability density function using a rectangular window of width 2 and I have 4 such samples with 2 samples at location x equal to 2. So, this is how I can estimate the probability density function. Now, let us see that instead of using rectangular window, if I use a triangular window, then what will be the situation? I use the same set of samples, one sample at location 1, one sample at location 2 and one sample at location 4. So, I have 3 samples and I assume that my rectangular window that I will use, that will have a width of say 3. So, I have to find out what will be the height of this window. This is the width. So, as you know that area of such a triangle is nothing but half into width, which is 3, into height. So, this is area of the triangle and area of each of these triangles has to be equal to 1 upon 3, because I have 3 samples and the total area of all the windows have to be equal to 1. Okay. So, the area of individual triangular window has to be equal to 1 upon 3. So, I put this is equal to 1 upon 3. And once I have this, from here I can obviously compute what is the height h, which is nothing but 2 upon 9. So, this is quite fine. Now, let us see that how, if I place these windows, use these rectangular windows, then how the overall estimated probability density function is going to look like. So, again I put it the same way. This is x, this is estimated probability density, which is p hat of x, this is x equal to 0, 1, 2, 3, 4, 5, 6 and so on. So, I have to put this triangular window at location x equal to 1, one of these windows. I have to put one window at location x equal to 2. I also have to put one window at location x equal to 4. So, let us place these windows. So, at location x equal to 1, I put a triangular window and the width of the triangular window is 3. So, that means that I will have 1.5 to the left side and 1.5 to the right side. So, it will be something like this. So, here if I have -1, I will have situation something like this. This is the rectangular window placed at location 1. Similarly, the triangular window placed at location 2, it will span from 0.5 to 3.5. So, I will have this triangular window, sorry, it will come over here. This triangular window will be like this. And I place one window at location 4 because I have a sample at location 4, and this window will span from 2.5 to 5.5. So, it will be like this. So, my final probability density estimate will be the sum of all these triangular windows. So, if I compute this, I will have a situation of this form. Say up to this point, I have only one window. From here to here, I have superposition of two windows, and then again up to this point, I have superposition of two windows. So, the kind of probability density estimate that I am going to have will be something like this. From here to here, it is single window, then up to this point, it will be like this. From here to here, it will be constant. Again, from here to here, it will be like this. Then again, it will be constant. Then it will follow single window like this. So, my final probability density estimate is given by the superimposed curve, which is shown in this blue line. This is the final probability density estimate. Now, given this, obviously, if I want to find out that what is the probability density at location x equal to 3, you find that probability density at location x equal to 3 is nothing but the height, the functional value of the final probability density, which is given by this value. Now, how do you compute this value? This is what conceptually is fine, but finally, I have to find out what is P x is equal to 3. This is what I have to compute. Now, if you notice carefully, you find that this superimposition of different windows placed at different sample locations is nothing but a convolution operation. So, what I am doing is, if I assume that every sample location, at every sample location, I have a unit pulse, that is a pulse of height equal to 1. And so, what I have is, I have a set of pulse trends. Okay? One unit pulse at location x equal to 1, one unit pulse at location x equal to 2, and one unit pulse at location x equal to 4. So, if this pulse train is convolved with my triangular window, where the shape of the triangular window is defined over here, then I will get this same probability estimated probability density curve. So, this is nothing but a convolution operation, and because it is a convolution operation, So, what will happen if I have multiple number of samples at a particular location? So, as before, if I have two samples at location x equal to 2, the height of that pulse I have to take is equal to 2. If I have a single sample at a particular location, the height of that pulse will be equal to 1, it will be an unit pulse. And if I have say k number of samples at a particular location, the height of the pulse at that location will be equal to k. So, I can have a pulse train of different heights, and once I have this pulse train, what I will do is I will convolve this pulse train with the window function of the kernel function, and this convolution output will be my final estimated probability density function, and that is what it is. So, once I have this concept, once I understand that this is nothing but a convolution operation, I have other way of estimating the probability density at location say x equal to 3. So, what I will do, because it is understood to be a convolution operation, I can simply put it like this. So, I will have this p hat x, in this direction I will have x, I have x equal to 0, 1, 2, 3, 4, 5 and so on. What I will do is I will put a window at location 3 of height, as we have said, height of this window is 2 by 9. So, I will put one such triangular window at location x equal to 3. So, this triangular window will be like this. And then what I will do is I will find out that what are the samples which are falling under this triangular window, and what is the value of this triangular window function at those sample locations wherever I have a sample. And this value, if at any location within this window I have multiple number of samples, say k number of samples, that value has to be multiplied by k. That is what is convolution, and add all these products together, all these products together. So, that is what gives me the convolution. So, here at location 2 I had one sample, at location 4 I also had one sample, but I did not have any sample at location 3. Height of this window, as we computed, it was 2 by 9. I have one sample over here, so I have to compute what is this height. I had one sample over here, I have to compute what is this height. And sum of these two heights is the estimated probability at location x equal to 3. So, I can easily compute that following symmetrical triangles. I have a triangle, this is half of the base. So, this is 1.5. The distance between 3 and 2, that is nothing but 1. So, this is location 3, this is location 2. So, this distance is 1. So, this distance is 0.5. This height, as we said, it is 2 by 9. So, I have to compute what is this height. So, now if you follow the properties of the symmetrical triangle, so you find that I get two triangles over here, one triangle is this and one triangle is this, and these triangles are symmetrical. Okay. So, if this height is h, following the properties of symmetrical triangles, I can immediately say that 0.5 upon, that is this length, upon 1.5 is equal to this h upon 2 by 9. Okay. So, I can immediately compute that this h will be equal to 0.5 upon 1.5 into 2 by 9. and this 0.5 upon 2.5 is nothing, 0.5 upon 1.5 is nothing but 1/3. So, this will be equal to 2 by 27. So, this height is 2 by 27, and by symmetricity this height is also 2 by 27, because this window is a symmetrical window. Okay. So, final probability density at location 3 will be twice of this 2 by 27, because that is this height plus this height, because these two are the samples which are lying within my triangular window. So, the probability estimate p hat of x equal to 3, this will be simply 2 by 27 plus 2 by 27, which is nothing but 4 by 27, right. So, this is what I have. So, the probability x equal to 3, estimated probability x equal to 3 is simply 4 by 27, which I can compute like this. If I use this one, okay. So, you find that the probability density, estimated probability density at location x equal to 3 is this one, which is 2 by 8. If I use a rectangular window, assuming that I have two samples at location x equal to 2. So, whether I use a rectangular window or I use a triangular window like this, I can always estimate the probability density function at sample locations where the samples are not originally present, and that is what is required for our application. Okay. So, all these sample locations where we have the samples, they are used for training purpose or for learning purpose. And once your system is learned, that is the probability density function is learned, using that estimated probability density function, I can go for classification of an unknown sample, right. So, this is what we have done in one dimension. What will happen in multi-dimension? If the features, instead of being a scalar feature, it is a feature vector, what we have done using the histogram based technique. How I will do it in case with the kernel based or window based technique. So, for simplicity, I will assume that our windows are rectangular windows. Okay. So, let us define a two dimensional space. So, I have feature vector x, which is of the form x 1 x 2, where x 1 x 2 are the components of the feature vector x. So, I am using two dimensional feature vectors, and I will use this as x 1 axis, x 1 dimension, and the vertical axis as x 2 dimension. Okay. Let us put some grid. Okay. So, these are the grids that I have, and suppose I have been given samples. Let us take some arbitrary samples, say 1 at location. So, I will put it this as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10, 0, 1, 2, 3, 4, 5, 6, 7 and so on. So, suppose I have been given samples of this form, say one sample over here, one sample here, one sample here, one sample here. Let us assume that we have got two samples here, then one sample here, one sample here, one sample here, one sample here. So these samples are arbitrarily distributed. So using these samples, I have to compute my probability density function using the kernel based technique. We have already seen how to do it using the histogram based technique. In histogram based technique, this entire x1, x2 plane will be divided into a number of rectangular bins, and for every rectangular bin, depending upon the fraction of the samples falling under that bin, I will compute what will be the height of the bar in that bin, and the height of the bar gives you the probability density estimate. Here I will use a kernel based technique or window based technique. So, let us assume that we use rectangular windows, obviously because this is in two dimensional case. So, this rectangular window will actually be a box. So, it will be something like this. And this box will have certain volume under the probability density surface. And as we have done in case of one dimension, I have to find out what will be the volume of every such box, volume under every such box. And that volume will be 1 upon the total number of samples which are given for probability density estimate. So, if I have total number of samples which is equal to capital N, then volume of individual box will obviously be 1 upon 1 by capital N. So, now here you see that I have got 1, 2, 3, 4, 5, 6, 7, because here there are two samples, 7, 8, 9, 10, 11, 12, 13. So, there are total 13 samples. So, I have N is equal to 13, and as I have 13 samples, volume of every box will be 1 upon 13. So, from this volume, I have to find out what will be the height of this box or height of the rectangular window function. So, to determine the height, I have to know that what is the base area of this rectangular window. So, again if I use that the base area, this rectangular window, let me assume here that this rectangular window is of base given by, let us say, 3 by 3. So, the base of the rectangular window is 3 by 3, that is area is equal to 9. So, I have 9 into height of the box, that has to be equal to the volume of the box, and this volume we have computed that this has to be 1 upon 13, because we had total 13 samples. Okay. So, I have this 9 into h is equal to 1 upon 13. So, obviously, the height of the box has to be 1 upon 9 into 13, which is equal to 1 upon 117. Okay. So, I have decided about what is my kernel function or what is my window function. Now, from this, suppose I have to estimate that what is the probability density at, let us assume, this location. Here I did not have any sample. What is the probability density at this location? Okay. So, we find that this location is 3, sorry, here I have made something wrong. This has to be 1, this has to be 2, 3, 4, 5, 6, 7, and 8. So, this location, this is feature vector which is 3, 4. So, I have to find out what is probability that x is equal to 3, 4. So, what I do is at this location I place this box whose base is of size 3 by 3. So, 3 by 3 means it will be 1.5 on this side and 1.5 on this side. So, this box will span from here to here and here to here. So, this is the box that I have. And now, I count that how many training samples are actually falling in this box. Okay. So, we find that the total number of samples which are falling in this box is given by 1, 2, 3 and there are 2 samples. So, total 5 samples are falling in this box. So, as total 5 number of samples are falling in this box, so what I have to do is this probability estimate P of x equal to 3, 4, this will be 5 into height of the box as we have computed, which is 1 upon 117. So, this is 1 upon 117, which is equal to 5 upon 117. So, this is the probability density, this is the estimated probability at location x equal to 3, 4. So, this is in the vector space. So, how we have been able to do it? Simply by placing the box and counting the number of samples within the box. It is equivalent to if I place a box over here, I place a box over here, place a box over here, place 2 boxes over here, then find out how many of these boxes are actually superimposing at location 3, 4. As I said that this operation is same as convolution operation. So, alternatively I can place a box at location 3, 4 and then I can find out that how many samples are falling within the box at location 3, 4. And those samples multiplied by height of the individual box, that gives me the probability estimate at that particular location, and that is what exactly I have done. Now, obviously, as we have done before, that this can be used for classification purpose. So, if I have assuming that these are the samples which are coming from say class omega 1 and I will have another set of samples coming from class omega 2 and I want to classify an unknown data which is maybe say same at location 3, 4. So, by considering only the samples from class omega 1, if I compute what is p hat x equal to 3, 4 and now because I am considering only the samples from class omega 1. So, that will be a class conditional probability density function. So, it will be p hat x equal to 3, 4 given omega 1. Similarly, by considering only the samples from class omega 2, I can also estimate what is p hat x equal to 3, 4 given class omega 2. And if the a priori probabilities of classes omega 1 and omega 2 is same, then out of this p of x given omega 1 and p of x given omega 2, whichever is higher, x will be classified to that corresponding class. If the a priori probabilities are not same, they are different, then p of x given omega 1 will be weighted by a priori probability p of omega 1. So, this is p of x given omega 1 into p of omega 1. Similarly, p of x given omega 2 into p of omega 2, which is the a priori probability. And out of these products, whichever is more, x, the vector unknown feature vector x will be classified to the corresponding class. Okay. So, this we have done in case of one dimensional features, in case of two dimensional features. And the same concept can also be extended in case of 3-dimensional features, in case of 4-dimensional features, in case of n-dimensional features. Simply by extending this concept of window function to 3-dimensional window function, to 4-dimensional window function, to n-dimensional window function, and so on. And because I cannot visualize this, I cannot draw that on a piece of paper over here, I will not discuss this, but the concept we have already explained when we talked about the histogram based technique for probability density estimation. Okay. So, it is the same concept which will be extended, which can be used for this window based technique for probability density estimation also. So, with this we come to an end to our discussion on probability density estimation, and you find that when we have estimated this probability density function, we have not assumed any parametric form of the probability density function. So, unlike in case of say normal distribution, where you have mean and standard deviation, which are the parameters of the probability density function, I have not used any such parameters. So, the probability density that you estimate, it is a non-parametric probability density. And in many cases, because we are not aware of what will be the parameters or what form the probability density function is going to take, this non-parametric estimation of the probability density function is extremely useful. So, with this I come to the end of our discussion of probability density estimation. Next class we will start some other topic. Thank you.